in the lecture notes are meant to be, done then, as you as you read. Okay, so that's the merge the on time, just to illustrate things that they're just being shown to you. So once again, this is a very important theorem. The takes the mystery out of the matrices. Okay, so that's how the matrix is formed if you know what linear operator does, you just ask it to do two things. Evaluate where 1, 0 goes and where 0, 1 goes, and then these two vectors are written. Once again, they're also two vectors, and each of which has a column. Remember that's the advantage of, or not advantage, as well as the of the notation that we frequently prefer, right? So the preferred notation is in fact AC. The column notation is actually is a preferred notation, and this one is BD. Okay. While the triangle notation is an abbreviation. So we do think of vectors as columns. Okay, so and then you take those two columns and put them together in a table, and then call it table of the matrix, and it works out perfectly as intended. So naturally it is when we have the operator and we know what it does, then we can see where it goes, and then we can write a formula for our matrix. Okay, so once again, some of the operators that we do know everything about, then they're easy to write the matrix. So you don't have to. There is really no mystery anymore. So once again, for example, number 3 here, horizontal stretch by 2 is this is the stretch. Horizontal stretch by 2. So 1, 0 becomes 2, 0, while nothing happens to 0, 1. Okay, so that's where the matrix comes from. The opposite here, you can see nothing happens to the 1, 0, but 0, 1 becomes 0, 3. That's how that 3 ends up at the bottom right. Okay, so horizontal flip, whatever is being flipped. So the horizontal vector is being flipped from 1, 0 becomes negative 1, 0. So that's where negative 1 merges in the matrix, and similarly for the other flip. The flip above the diagonal, remember, so that's literally, once again, x becomes y, and so 1, 0 becomes 0, 1, and vice versa, and that's how we did that twisted matrix is, where it comes from. Okay, so all right, so these exercises. So let me think these are right. All right. Okay, so rotation is the most interesting one that is impossible to guess, even though we did one rotation probably. But this is what the rotation matrix is, and so something that does not exist in any way in the one-dimensional case. But this is the two-dimensional matrix, and it's made of if angle is given, you just plug them in, and the algebra is entirely. So if you know the basic trigonometry, then looking at the where the matrix ends up. So if you start with 1, 0, and you rotate alpha degrees, and then you have this triangle, and remember that's if this is the unit circle, then remember that the coordinates of that point on the unit circle are the sine and cosine of the angle. Okay, so that's the definition of sine and cosine. And so that's the matrix. As you can see, there is certain symmetry to it. Cosine emerges twice on the main diagonal, and sine with the negative sign emerges on the other diagonal. Okay, so this is 45 degrees. So if you want to test it, this is how you test it. Plug in the numbers here. I take pi over 4 being the angle, and then I end up with the matrix, which is right here on the left. And then indeed I plug it into my spreadsheet, and it rotates 90 degrees, 45 degrees. My ellipses have been rotated. Okay, so all right. So just one thought about three-dimensional and high-dimensional linear operator and matrices is it applies exactly the same in the exactly same manner. You can guess if we take this theorem over here, a very general theorem. A matrix of a linear operator is fully determined by the value of its basis vectors under the operator. This is Rn. Once again, if you try not to use the dimension specifically and then rather do the use words, okay, so no formulas, especially no coordinate representations of vectors, then your words designed in such a way that you speak of in the n-dimensional case anyway. So that's what we are facing here. So if we turn around and then realize indeed that the formula, I was about to fix it, but there's no need to fix it. So already it is written in for dimension, arbitrary dimension in space. Okay, so then and as an example, what about three-dimensional rotation? Okay, so that's what I'm asking here. What is a three-dimensional rotation anyway? What does that mean? Does it need to rotate in three dimensions? No, that's not that. No, that's a flip. The x and y interchange. That's a flip. That's not a rotation. The rotation, literal rotation, literal. So by analogy with this is rotation. Rotation. I guess I don't have a picture here, but well, I hope the rotation is nothing. It's not something controversial, but this is the example of rotation 45 degrees. Okay, so the whole plane it's held by the origin and then rotated around that origin. Okay, so that as a piece of paper, whatever is drawn on it, then also is rotated. So that's what the picture shows. Okay, so the domain with the curves on the left, the codomain with the resultant curves on the right. Okay, so we can easily figure out using the theorem that we have what the matrix would look like for the rotation in dimension 3 if we just knew what that means. What is the rotation in dimension 3 anyway? Does it make sense? How do you rotate? Can you imagine rotation in dimension 3? So rotation for you. Okay, so it can be done. You just need to be specific about certain things and the axis. It's still the dimension. The rotation in dimension 3 is still two-dimensional. Okay, so there's still an axis. So imagine a ball, spinning ball. Okay, so in 3 dimension, right? And so an important thing. Whatever it's baseball or tennis, the spin makes a difference. So what is a spin? Once again, there's an axis and then there's a rotation. Okay, so around that axis. So in other words, the motion is still two-dimensional. The rotation itself is two-dimensional. So meaning that so once you chose the axis, then the plane perpendicular to that axis will be within which the rotation will be recorded in a manner exactly similar to this. So as an example, not going into details, this is I'm looking at rotation around the z-axis. So that's the easiest one. So we have a screwdriver or some kind of some kind going in. Okay, so rotation, it's not moving. If you want to add, by the way, rotation, then motion of that screw, then you could. But here we're just interested in rotation. So once again, just look at where each of the three basis vectors go, E1, E2, E3. Okay, so once again, the rotation is still within XY plane, so everything that we did here applies. If we're doing, we cannot do one dimension at a time or one axis at a time because they're actually intermixed. But fortunately, X and Y are even though intermixed, this one is not. Okay, so nothing is happening with along the z-axis. Okay, so as you can see, 0, 0, 1 remains there. But what happens to the other two? Well, we know what happens to them. The first two coordinates change in the manner that we already know. With some once again, the third coordinate is not changing because the rotation within the xy plane, which means that 0 remains 0. Okay, so that's what we see here. Nothing is happening here. Okay, so and then I take these now three vectors, and once again I think of them as columns. Okay, and I take these columns and combine them together into a 3 by 3 matrix. So as you can see, the old matrix for dimension 2 is still visible there as that square, but I still have a bunch of zeros. So that bunch of zeros indicate that as far as z is concerned, nothing's happening. Okay, so you can easily write matrix of rotation about other axes, but if you were to do a rotation about any other axis that's less than obvious, then it's less than obvious how to do it. Rotation along the diagonal, for example, how do you write it out? It will be way more complicated. There will be any zeros. Okay. So any questions about rotations? Okay, so so example. So the challenge is, so we know what we know, how to get a matrix for a linear operator backwards is not so easy, and that's really what we're studying. So if we have a matrix, so this is my function, okay, from R2 to R2, x's, y's, to u's and b's, and if I write the matrix, it's not that recognizable in any particular way. So I should be able to it does not fit. It's certainly not a rotation matrix. So experimentation will tell us what this is, and it does suggest that there is some kind of rotation, but also in addition to rotation, there is a stretch. Okay, so that's what we're seeing here, right? So I drew ellipses just like in this example over here, and the rotation now is visible, but also the size has changed. But is it a uniform change or not? And what is the rotation angle is there is also not entirely clear. So all of these things that we want to go backwards, that's the inverse problem. Is when if we have the matrix, the operator, and the matrix, and we are maybe even allowed to experiment with it, but then the end result is supposed to be a description of the linear operator in terms of that we know. So stretches, rotations in let's in chronological order, flips, stretches, and then rotations. Okay, so in dimension 2, fortunately, things are not that hard, but these 3 things are pretty complicated. If you combine them together, this is clearly at least 2 of them are present. There is no flip, right? You can see that there is no flip. There's no flip. Do you see a flip? How do we know that there's a flip or there is no flip? Yes.
Let's go in the same direction.
Right.
I imagine there's.
Yeah. So careful look at the directions of those curves. Clockwise remains clockwise. Counterclockwise remains counterclockwise. So there is no flip. Okay. So that's what the flip is. Okay, so all right. So let's so once again, that's the question, how to do it, how to decompose and represent the linear operator in terms of these simple pieces as a composition. Let's face it. So like this maybe. Okay, so this here is a stretch and then rotation. Okay, it's possible, or rotation, then stretch. It makes no difference. If the stretch is uniform, then it doesn't make any difference. So that's would be ideal answer to about what does this operation do. Ideal answer would be this. Say stretch by this coefficient of coefficients, and then there's a rotation through this angle. Okay, so that's the ideal answer, but we are not really entirely in the position to do that in this class, but let's do the best we could. But I think it is just as important, however, to look at the examples that are simpler, but they are actually n-dimensional. So let's take some of these simple matrices in the n-dimensional case. So once again, how do we build a matrix? From if we have a description of a linear operator, well, the examples are pretty much starting the same way as we just started today. So once again, this time there are n vectors. Okay, so these are the n vectors, and these are the ones. So this is E1 and this is En. So it starts with each of them has a one and then a bunch of zeros. Okay, and then so that's why you have n of them, and then you just see where they go under the linear operator. So if the operator is 0, everything goes to 0. And so that's every output is a 0. So you combine these outputs and you have a zero matrix. Okay, so that's it. Those dots may look a little bit intimidating. So that's just if you just go to dimension 3 and you see it's not really that complicated. So if you draw, in fact, if you drop the dots, what you're going to get is dimension 4. Okay, so there. The point is, of course, if we can study all the dimensions all at once. Okay. So the identity operator is everything, every vector stays, every basis vector stays. We're not trying to deal with all the vectors at the same time. We're dealing with only those n basis vectors. And so the basis vectors remain. And so we just combine, these are the basis vectors. This is E1, this is E2, En minus 1, and this is En. And so as you can see, they're combined together intact, and then they form our identity matrix with ones on the main diagonal. Surged by 2 of the first vector, so everything is the same. Once again, everything kind of is built from the identity matrix. We just know what happens to one particular dimension. Something does happen. Elsewhere, nothing happens. So which means that everything remains the same, and the only change is here. Okay, so if we decide to stretch the first axis by 2, or along the first axis by 2, then that 2 emerges, but nothing else. So that's the new part, and the rest is the same. Flip about the first axis once again. This one stays, and this one it emerges, -1. That's the flip. Central symmetry. Okay, central symmetry more interesting because every basis vector is flipped, which means that wherever you have a negative sign, wherever you have 1 becomes -1, and therefore once again every 1 becomes a -1. Well, here's a question for you: is there a flip? What?
So dot just means it's separated into 2 axes.
No, that means that there are more. We just don't know how many, because n is unspecified, which means that we cannot write the whole thing.
Any amount of axes.
What?
It'd be any amount of axes.
Right.
Okay.
So this is you can see already 4. You can insert 1 easily, like this. Hold on a second. Then I would have -1. If I want to go with dimension 5, then this is what it would look like. Right. So you where have you seen that before? Outside of this class? Where? In math or outside of math?
I mean, you could use it in writing too, if you're listing out something and you just.
Well, yeah, it doesn't have to be anything scientific. You just have a list, and then you just dot, which suggests that we just continue on with a pattern that's supposed to be obvious. So if I started with zeros, then dot indicates that zeros continue on. Okay, so that's what the in math you see it in calculus 1. Every time you have a sequence, after all, what these are just sequences, finite sequences. So if you are familiar with the notation and the kind of customs of dealing with sequences, that's what dot indicates. Naturally, when you do computing, then dot is not allowed in a way, because that's how people write it. They are behind. If you want to do computing in that manner, you use the idea and do a computing, then dot is just a cycle. Right, so just there's a cycle here, so 1, and then a cycle repeated 0. Zeros are being repeated, and so then the computation and the forming that table over there, and it is once again, if you are doing in computing, and you could have n as a parameter. There is no trouble with whatsoever with that. You have a parameter, and then the cycle runs 4 times, 5 times, or unspecified number of times, which is, and then you choose whatever n is necessary, and then your cycle runs as many times as necessary, depending on the circumstances. So that's the similarity or overlap between computing and this kind of mathematics. Except, like I said, we write it on a piece of paper with a pen. We have these dot, and then if you're computing, you are giving command to the computer, so you have to be much more specific about what is supposed to happen. Okay, any more questions about this? We're not doing a lot of n-dimensional stuff, but if you a taste for it, this probably makes sense. So any questions about this? What is the meaning of a flip of that? As you can see, central symmetry, and that's a fair question to ask. Is there some kind of flip there? So does the orientation change? That's the question that okay, so in dimension 2, it's a circular curve that goes clockwise and then become counterclockwise if you flip it. Okay, what in dimension 3? What's the analogy of that? You can't flip in change the orientation of the third-dimensional space to the opposite. Just look in the mirror. Everything is flipped there. So whatever writing is now going from left to right, and everything is a mirror image. It is like behind the mirror is a three-dimensional world. Okay, which area where everything is the opposite. And so your heart is on the right and stuff like that. So it is a three-dimensional situation. Okay, so that equation does make sense, but it is more mathematical than anything else. So it's so does it make sense, and how do we make sense of what orientation means, what the flip is, and these two worlds are separated. So if you in the mirror, you cannot just walk around the mirror and then join that guy in the mirror, because everything is different. Like I said, it's a different world. And so imagine that not only the bodies have a wrong symmetry, but also molecules have wrong symmetry. So the mirror image of a molecule is a different molecule possibly. So it's an issue, and so that's the question is for us to worry about, maybe if we go deeper into the mathematics. Okay. Okay. All right. So the questions really we're asking are way simpler, and that is the question how do we know that a linear operator is one-to-one? Remember why we care, because the inverse. So if you have a linear operator, is there an inverse, and then we need for that the operator to be one-to-one, and so that's what we care about. Since everything is linear, everything is way simpler than in general situation. So actually, we care about we can just check the zero. Okay, so once again, this is one-to-one. I'm sorry, this is not one-to-one. Okay, so that's the general illustration of not one-to-one, a generic. And then if I go with linear, turns out that I only have to consider zero here. So why so? Because zero always goes to zero. Okay, so a zero always goes to zero. Okay, that's just the we talked about that a little bit. Okay, so zero goes to zero, which means that if there is another element that also goes to zero, it's not one-to-one right away. Okay, so the more subtle question is that's the only thing for us to consider. We only as the output we of where we can express our concern about is it one-to-one or not. That's the only output that we have to consider. Okay, so once again, the question of one-to-one is there should be exactly or no more than one x for each y, or for each y. So once again, generically, no more than one x for each y. For each y. But we say, because we're doing linear algebra and things are way simpler, we say just for y equal to 0. Okay, so we need to verify that condition. This is the condition of one-to-one, generically expressed. And then we say, well, we don't really need to check every y, but just one, y equal to 0. And once again, if it fails, it fails. It fails. It doesn't matter where it fails. But the point is y actually works out no matter what for the rest of them. If we checked y, it turns out we don't have to check anything else. So it is kind of a linear thing, and that is I'm not sure how much it needs to be explained here. the situation is not generic. So linear operator have this very simple structure that verifies that verification of one-to-one requires this exactly this. The equation f of x equal to 0 has only has only that zero solution. Zero solution is a solution always. Is there another one? If there is no other one, that's it. We have that settled. And the answer is we've seen this idea a little bit of this. So so this is a typical not one-to-one operator, and this is what if this is 0, then what makes it not one-to-one is this. A whole line of xy's is collapsed to the origin. Okay, so that's how we know that how that linear operator is not one-to-one. Not just one x. Over here I have an x, and this x goes towards 0 under my linear operator, but also a bunch of them. Okay, so on the other hand, this is not possible to have two numbers x and y going towards 0 towards rather anything else like this. So if I have f of x is equal to f of y for two x's and y's not equal to each other, then they not necessarily zeros. So a little, very little, very short argument demonstrate that there must be an element that goes to 0. As you can see, I factor f out. Okay, so I move stuff to the left over here and then factor f out by linearity. I'm using linearity. It does not work with any other function, but with linearity, we can pull everything inside of f, and then turns out f takes x minus y, let's call it z, to 0. Okay, and so then we prove that indeed, if it's not one-to-one, it must be not one-to-one, we exhibit non-one-to-one behavior with 0. Okay, so it will hit 0 if there is any in one-to-one capabilities here. This is what I'm referring to here, maybe. So this is say x, and this is y over here. Okay, so and this one is say z somewhere. Okay. Okay, so if there are two x and y's coming together to the same point right here, maybe. Okay, then through this algebra over here, we demonstrate that there is another element z that actually goes to 0. Which means that yes, we don't have to care about anything else but the 0 in order to test whether our linear operator is one-to-one. And there is especially in the case of two-dimensional case, there's not much that can happen. If it's not one-to-one, is either it is entirely the collapse, everything is 0, or it is a projection. So you just need to find that line on which everything collapses. In high dimension, there is more things that can happen. You can collapse on a line, but you can also collapse on a plane like this. Okay, so that's also. So naturally, the higher dimension, the more possibilities are there. But nonetheless, this theorem once again fully applicable to the n-dimensional case. The algebra, as you can see, I'm not making any reference to dimensions. And that's why whatever I write, the algebra I write, following the rules of linear algebra, then it works out perfectly. The proof is totally solid. Okay. So then that's what we need to establish. That 0 goes to 0. So this is a non-generic, specifically linear situation here for one point. It's the problem is general. It does not necessarily about linear algebra is the existence of the inverse. You know, you invent square root, you invent logarithm, you invent arcsine or cosine, all of that. So the function has to be one-to-one in order for us to invert the function. But in linear algebra, I think simpler, and what we make up with the dimensions, obviously. So dimensions what makes it complicated. Okay. So, all right. So remember this fact. So a function being one-to-one, if f of x is equal to 0 for some non-zero x. Okay. So this x is not equal to 0 right here. So this is 0. This is this 0. And then x is not equal to 0. So that's what indicates that there is a not one-to-one. Okay. So, all right. So the determinant, the idea of the determinant is right here in this sentence. Can be determined without examination whether linear operator is one-to-one. one single number, and we call it the determinant, and we jump straight to dimension one when the answer is very simple because the function is equal to is mx. There's only one linear function, mx, multiplication by a number. Okay, and then m is the determinant. So whenever m is not equal to 0, like this, okay, so this function is invertible, and so it is 1-to-1. The only exception is this one. M is equal to 0, and it is not 1. Okay, so that's the whole story in dimension 1. So it does work out. The question that we ask you here, the answer for dimension 1 is very simple, and it's as expected. One single number tells you whether or not the function is invertible, and that's it. So in dimension 2 is way more complicated, but nonetheless we can sort it out. Okay, so once again, projections, the examples that are not trivial examples of functions that we want to stay away from. Okay, so let's look at some examples. One-to-one. So is it one-to-one or not? The experimentation usually indicates whether or not you have one-to-one or onto. If so, if these ellipses, whatever happens to them, if they still look like ellipses, even though all distorted, nonetheless, we know that the whole plane was covered with those ellipses on the left, and the new ellipsis on the right is covering the new plane. So that's what one-to-one means. So if it's actually more about onto that they cover the whole thing, but nonetheless, the fact that these ellipses, if they did not intersect in the on the left, they do not intersect on the right, and that's one-to-one. So no intersection. And that's 1-to-1. Okay, so you can, from experimentation, you can tell what it is. This is the typical example is this. So circles on the left, and then under the linear operator, a very simple operator. And once again, I carry out the same plan. I do a spreadsheet, and then we did it before. The circles on the left, they are taken, and they all lie within this line. Okay, so that's a collapse. That's a projection, and that is not one-to-one. So there will be several of them with that several axes going to the same point on that line. But let's ignore it and suppose we already know that is not one-to-one. Okay, and I'm comparing that. We know that at the top right here, this is one-to-one. Okay, so can you see the difference between the two matrices? What would suggest to you with the second matrix that it might not be one-to-one? The second matrix has a certain pattern. You see a pattern? Regularity, dependence. You see a dependence with the second vector. They colored on point, on purpose. 1, 2, 2, 4. What's the pattern? Multiplication by 2, that's right. So in fact, I take 1, 2 and multiply it by 2, I get 2, 4. That's the dependence. That's the dependence, and it is important. Why? Why is it important? Yeah, but you remember what these vectors stand for. The red one and the green one. What we started talking about today. The columns of the matrix stand for what? The columns, we started the discussion today with that issue. Vectors, where they come from? Very beginning, and we actually started at the end of last time. They are where the unit vectors go. So 0, 1 goes to 1, 2, and I'm sorry, 1, 0 goes to 1, 2, 0, 1 goes to 2. Okay, so the fact that they are multiples of each other, so turns out multiples of each other, which means that the two vectors, that's what's going to happen. So once again, 0, 1, or the red one, goes to the red one. The green one, 0, 1, goes over here. Okay, so and then remember with the idea was that we think of the two basis vectors, those on the left, as kind of wooden planks, with the rest of the plane as a fabric stretched on it. Okay, like on a frame. And then we control, and then we look where those planks go. And it turns out that two planks that used to be like this, they became like that. Okay, so then what's the fabric? Well, what happens to the fabric? And the answer is it's still here. It's also remains within the plane. So this is not covered. So everything outside of the line is not covered. So the whole, and that's the projection. The projection, the whole plane is collapsed or projected on that line, and that makes it automatically not one-to-one. Okay, so and if you want to be specific, then probably if this is bad. So like I said, where's my algebra here? So we can probably think of, well, let's think of two vectors that go to the same place. So even though the two basis vectors do not come together to the same, okay, nonetheless, we can point out a vector that goes towards 0, for example, or two vectors go to the same place. So example that it's not one-to-one. Okay, so we need f of say x equal to f of y. We need two specific examples from the examination of the picture or the algebra that probably let's do the algebra that indicates that two vectors come together. Okay, so and that's really not that complicated if we just concentrate on let's y be 0, 1. This is 0, 1, and f of 0, 1 is, as we know, 2, 4. Okay, so how about x I choose to be twice 1, 0. In other words, 2, 0. Okay, where does 2, 0 go? And 2, 0 go, it goes to, we know where it goes. It goes to 4 as well. Okay, so that's the idea that I come from the observation that 1, 2, and 2, 4 are multiples of each other. We know exactly what that multiple is. It's 2, and then so we know that if we just take a vector to be here twice 0, 1, where does it go? Where does twice 0, 1 go? And it goes to the same place where 0, 1 goes. Okay, so based on this observation. This is the observation that we made. The dependence between the two columns, it's a multiple. It's very simple. It depends in dimension 2. Then we know that then if I take multiple of the first basis vectors, multiply by 2, and where does it go? According to this, it will go to the same place as the second basis vector. So that's creates right away the fact that it's not one-to-one. Okay. So it's more complicated than necessary, especially because it's kind of ad hoc rather than systematic analysis. So we actually, for observation and insight, discovered that these dependence between the two columns, which is really not what we want to do. So it's just an illustration of what the nature of the problem is. Yeah. So basis vectors, the difference between the two cases. This one is one-to-one. This one is not. The basis vectors go to multiples of each other. The values are proportional to the vector 1, 2, and then that's what we have here. And as I pointed out, the whole line of vectors, you can now look at it, and that's the analysis that we're after. The green line, you see the green line on the left. The whole green line, actually, the dotted line collapses to 0. Okay, so the red line is where everything lands. Okay, and then it does it. That's how it happens. So we push everything towards the green line, but specifically, especially everything moves, but where the green line specifically moves towards entirely towards the origin. Okay, so that's just an illustration, and the picture on the right does not give it credit because everything collapses. You don't see where every line, every curve goes. Okay, so let's do more algebra. But the word, some terminology, it's called a singular matrix if columns are multiples of each other. 2 by 2 matrix, that is singular, and we know why it's singular, so it's not a good one. There is no inverse. Okay, so all right. So if our matrix is A, B, C, D, then what we're saying here, singular, that AC is equal to BD multiplied by X. So it doesn't matter what X is. X doesn't matter. We're only saying that there is such a thing. Okay, so then we ask ourselves under what circumstances matrix is singular, and we're relying on the existence of X. We can do certain algebra with it, and that's what we do here. So we take my equation here and rewrite it and break it, my vector equation, into equation of numbers. So A is equal to XB and C is equal to XD. Okay, and then what do we do? Let's exclude X. Let's eliminate X from the equation. Because X exists, we can eliminate it. If X did not exist, this whole plan falls apart, and that's why whatever we're doing only works out for a singular matrix. So then it turns out to be not too complicated. So AD, I multiply the first by D, first equation by D, and the second equation I multiply by B, which gives me these two equations. Okay, AD is equal to XB and CB is equal to XBD in order to have a cancellation on the right. Okay, when I do subtraction. Okay, I do subtraction, and then on the right I have 0, on the left I have AD minus BC. And that is exactly what the determinant AD minus BC is the determinant. Because what the logic, the way we logically proceeded, we assume that the matrix is singular. Okay, that's the assumption was the singularity of the matrix. Okay, so that's the definition of singularity. Okay, then we assume that such an X exists, did some simple algebra, and we concluded that AD minus BC is equal to 0. Okay, so then that's exactly what the logic was, meaning what? So singular means that AD minus BC is equal to 0. Okay, so that's what we have demonstrated singularity. Okay, so and indeed that's how those 4 numbers of our matrix are combined together to produce a number that tells you something very specific. And that's, once again, is the function singular or not? Is it invertible or not? And is it one-to-one or not? So that's the definition of the determinant. So as you can see, it's seemingly a random combination of those 4 numbers, but there's a certain pattern there. As you can see, we take one diagonal and we take the other diagonal and subtract. And we have multiplication here. Okay, so once again, matrix is singular if and only if the determinant is equal to 0. Okay, so the plan is, and we already know that singular means not one-to-one. So the problem that I put forward in the beginning of the section has been solved, right? So then matrix is not one-to-one if and only if the determinant is 0. So 0 determinant is bad, as you can see. So if good is a matrix that is invertible, then determinant equal to 0 is not a good thing to have. So there's certain algebra to demonstrate the converse, especially. So we only demonstrate in one direction. So if it is singular, then it is determinant equal to 0. Backwards a little bit takes a bit more work, but so I encourage you to read this work. Okay, so finish the proof. Okay. Okay, so this is probably once again a glimpse into Rn. So this is all R2, the 2-dimensional case. And then maybe it's hard to guess how it's going to proceed in a high dimension and the whole logic of determinants in high dimensions. But we do notice that determinant is an alternating sum of the terms, each of which is the product of the matrix entries, taking exactly one from each row and exactly one from each column. So if you look here, in the alternation, what's the alternation? Alternation is plus and minus. That's what we mean by alternating sum. Okay. Secondly, AD and minus and BC, what are they? They are once again they multiply, but they take in one from each row and one from each column. Okay, so that's what. Then the only way to do it is well, the two ways to do it. One from each row and one from each column. The only way to do it is two ways to do it is AD and BC. Okay, there are only two ways to do it. When you do so, as I said here, so from one from each row, exactly one from each column. Okay. In R2, n is equal to 2 ways. In n equal to 3, this is what happens in n equal to 3. And how many ways can we pick terms, one from each row and one from each column? And the answer is actually 6. Okay, so these are marked. So look at the blue ones, that's one term, red ones, another term, green one is the third term. Okay, so the total of 6 terms that you can write, different terms. Once again, look at the patterns of green, red, and blue. Each has exactly one entry from each row and one and from each column. Okay, so but as you can see, there are a total of 6 ways to do it. Equal to 3, 6 ways. And then that number, as you can see, grows. 2n minus 1 ways to do it. And so indeed a 3, hold on. So if I have 3, 2, hold on, why is it 4? I don't think my formula is correct here. My formula here is correct. So n 6 ways when is equal to 3, and if I plug in, I have 2 times 2. It says it's 4. So I don't remember where my went from here. And if I 2, it's 2. Okay, so it works for 2, but not for 3. So that's a typo here. Since we're not using it, so it's not a big deal. But so just the illustration of dimension 3 is once again suggests that things become complicated. Okay, so and it does not go into such a linear way in a simple way as one would think. So 6 terms, as you can see, main diagonal, then off main diagonal this way and then that way, and you can combine these terms and you can compute the determinant, which has exactly the same property as we just indicated. So it gives me determines whether or not the function is singular, the operator is one-to-one or not. Okay, so. All right, so then so this is let's put it in more precisely in a precise language. So we're looking at a function with a linear operator f, and we set it equal to 0. It's called a homogeneous equation. Okay, and then we ask ourselves, is it solvable? It is solvable always. Once again, it's solvable in the sense that x equal to 0 is a solution. But are there more? That's what we have been asking. And the answer depends on the determinant. Once again, so this is there another one, x? Is there another one? If there is, that's the bad news. We want to have only one. If there is an extra x, it's not one-to-one, and it's not invertible. Just look at those arrows. If I flip the directions, that's not a function anymore. Okay. So the question becomes, are there any non-zero solutions to that equation in the box up there? And that will answer the question about is it one-to-one or not. In dimension 1, once again, our function is simply multiplication, and then solving the equation f of x equal to 0 can only happen when m is not equal to 0. If m is not equal to 0, then you solve it by dividing by m. So here, divide by m. Okay, and so you have mx is equal to 0 divided by mx is equal to 0, right? So that's the logic. Unless m is equal to 0, then the solution cannot be, you cannot solve for x. Or rather, if m is equal to 0, then what happens? 0x is equal to 0, solve, what do you get? No,
You divide by 0, right?
no, well, I'm not telling you to divide by 0. If you decide to solve it by dividing by 0, that's your problem. Maybe you just took a different wrong route. 0x is equal to 0. Like I said, we need to solve it, but I'm not asking you to divide. You don't have to divide if you don't have to, you don't want to. So what's the? So for x. How about 1? What?
Could be anything.
That's right. That is the answer. All x's. All x's. Any number x you plug in there will give you the correct answer. You have 0 on the left always. You have 0 on the right always. So this is always true, which means that whatever x you have in mind, it will be a solution. Okay, so so then what it means is clearly it means that it's not 1-to-1. Okay, so that's the logic we have here. Just to dispose of the simplest case of dimension 1, and then because there are no projection, there's only collapse. The constant function is the only exception from the rule. The linear functions this is the all linear functions in dimension 1 are plotted here, and they are all invertible with the only exception of slope equal to 0. In which case, like I said, the solution has infinite many the equation has infinite many solutions. Okay, so now we're in the same place, but in two-dimensional case, in which case we have this case which is kind of not as bad as the collapse, but not as good as we wanted because once again we have the function is not 1-to-1, and so for example, if I take this point and that point, they end up at the same location over here. So it's this one, the projection is not 1-to-1. So how do we detect it? Detect this behavior, and the answer is once again the determinant. Okay, so so that's the answer. We have a 2x2 matrix, and the determinant is not equal to 0 if and only if the solution set consists of only 0. So once again, if you forget, it's easy to forget that determinant equal to 0 is good. Determinant not equal to 0 is bad, and not equal to 0 is good. So once again, remember M. So remember M for dimension 1. So M in dimension 1. This is M for dimension 1. This is so determinant equal to 0. That's the exceptional case in dimension 1 is determinant equal to 0. The function is constant. So when it's not equal to 0, that's the slope. Okay, so that's what the equation is mx. So m is the slope. So slope positive, good. 0 or not equal to 0, positive or negative is good, and equal to 0 is bad. Okay, so and now the slope is, well, there is no slope because we are talking about something that is hard to even visualize because you have two dimensions. You have two dimension here, two dimension there. Where is the slope? How many slopes are there? So we have to speak in different terms. We speak in terms of transformations, and but the logic remains the same. So the 0 is bad. Okay, so 0 is bad. It's kind of gives you some direction in which. So if I want to explain informally, there is a 0 slope somewhere, which indicates that it's not going to be 1-to-1. Okay, so okay, so once again, determinant tells us when it is equal to 0 that it's not 1-to-1. So as you can see, the algebra is fairly well, it looks involved, but really it is linear. So there is nothing comes up other than just a linear algebra. So we don't even multiply x by y. We have x and y. X multiplied by numbers, y multiplied by numbers. So that's what we're doing here. We're taking our system of linear equations and trying to figure out what the what it means to have a solution that's not equal to 0. And then as you can see here, look at it, how determinant automatically emerges in the same manner as it did before. Is this subtraction over here, and the determinant automatically emerges. Okay, CB minus I multiply this one by C and this one by A. and this by A, and then when I carry out the subtraction, what do you know, the determinant emerges automatically. Not so easy in high dimensions, but in dimension 2, yeah, it is still recognizable how doing algebra with the two equations actually automatically produces the determinant. So let's compute a few determinants and see if there is a pattern there. So the zero operator determines equal to 0, okay? So it is an indication that the operator is not one-to-one. So once again, so the square that the plane, where does the square of the plane is taken, and the answer is taken to a point. Naturally, that's to be expected. The identity operator, the determinant is 1. Okay, so the determinant is equal to 1, which indicates, as we know, that it is 1. Okay, so but also it's not just not equal to 0, but also there is more to it. Because it is nice to have 1. It's nice to have 1 when it's neither positive nor negative. But if it is negative, then we have a rigid motion. Okay, so the determinant actually is still to be, well, we can guess the geometric meaning, or what's the meaning of the determinant. And the answer is, we could guess once again if we project back to the dimension 1. Oops, where am I? Okay, so if we go back to dimension 1, what is the meaning of m in terms of transformation? So okay, so we have here f from equal to f over f equal to mx. Okay, and then we're thinking of f as the transformation of the line. So once again, I'm going back to dimension 1 just to guess the meaning of the determinant, not what it tells us, what it determines, but something maybe it contains more information. Okay, so what's the meaning of m? What does multiplication by 2 do? To the line. Every x multiplied by 2, how do we describe the transformation? Stretch. Indeed, the stretch is the determinant is then the stretch coefficient. Ideally, if negative 2, by the way, is also the stretch coefficient of 2, so negative, we also know what negative means. A negative means negative anything means a flip. Okay, so these are two things that we can detect from the slope. Very, very transparent what it means. So larger than 1, it's a stretch. Less than 1, it is a shrink. If it is, that's the absolute value of m. Probably would be a good way to look at the absolute value of the slope as a transformation. What its meaning? Its meaning is the stretch coefficient. When then you take a negative number, if there's a negative sign there, there's a flip. So now if we take these ideas and take them to dimension 2, well then that's think about it, what it does. The identity operator has the determinant equal to 1, no stretch. Okay, and that's what rigid motion is. Okay, for example, rotation has no stretch, and that is a rigid motion. And we also know that -1 indicates probably a flip. Negative 1 indicates a flip. Okay, so these are the clues that we can collect about the linear operator without actually carrying out the experimentations, but rather looking at the determinant. Okay, so flip about the y-axis. Look at it to confirm these conjectures. To confirm the conjectures, take the flip about the y-axis. It has the determinant negative 1, 0, 0, 1. The determinant is a negative 1. Okay, so negative 1, that's a flip. So if we did not know what that linear operator did, we would have discovered nonetheless that there's a flip there. Okay, so the negative number suggests a flip. So like this, what the flip is. Negative sign is indication that operator changes orientation. So that B, it was easy to think about a flip in a one-dimensional case. This is my x-axis, and then what it does this. Okay, so that's what the flip does. It changes the orientation of the arrow points in the opposite direction. So it's more complicated in the two-dimensional case, but nonetheless, if you have to take a different look at it and think about its whole plane with something drawn on it. And for example, that letter B written there in the box, well, it turns out to be different locations. It's also pointing in the it now a mirror image. That's what mirror image does, and that's what negative sign does. Okay. This one is interesting. Central symmetry gives me 1. Central symmetry with 2 negative 1s on the diagonal. When you multiply and compute the determinative, the answer is 1. What does it tell you? The determinant of the central symmetry is 1. What would, if we did not know, well, I mean, we do know, we don't know the number, we know the central symmetry does. What the conclusion do we draw from this? What's so special about central symmetry that now is reflected in the fact that the determinant is 1? Well, yeah, the mirror symmetry is also symmetrical. The number 3, it's also, that's a symmetry, literally the definition of the thing. It's just different symmetry. So it indicates that it's different. That's what really what it says. The difference between the 1 flip or 2 flips. Okay, the flip, the mirror symmetry. That's a mirror symmetry. And this is the central symmetry. And the central symmetry is 2 mirror symmetry, which means that what? 2 symmetries, 1 flip, the other flip. What happens? Same. So the screen was up and it's still up. If you do 1 flip, you switched it. Okay, so everything becomes the orientation changes. But if I do 2 flips, turns out I'm back. And so there will be no picture like this. Nothing like this. And in fact, if you remember that, actually, then if you start thinking that, so it's there is no flip, that's the conclusion that we make. And then you start remembering that actually that's what it is. It's this 180 degrees rotation. That's what a central symmetry is. And so instead of doing 2 flips, I could just do this. And I'm back. Okay, so it's the same. The look is the same. The clockwise remains clockwise, and counterclockwise remains clockwise. Like this. Okay, so there is no change of orientation. If you flip twice, then you're back. So there's only one way. There's only 2 orientations, and you switch between them. Okay, so next, this is a lambda and mu. I put them on the diagonal, and the other 2 zeros. We know that what that means. It means there are 2 stretches: the vertical by lambda, horizontal by lambda, and vertical by mu. And the answer is that the determinant is lambda times mu. So what's the meaning of lambda times mu? Let's take a specific example. 2003. The determinant is equal to 2 times 3, 6. Can you tell the meaning of 6 here? Horizontal by 2, vertical by 3. What's the meaning of 6? Oh. To what? The area. Exactly, yeah. So you can speak separately of 2 and 3 different 2 stretches. Length horizontally doubled, tripled vertically, but what's the meaning of 6? That's the change of the area. Okay, so you was indeed then 1 square, the unit square 1 by 1 becomes 3 by 2. Okay, so it's the opposite here. I think I'm 2 by 3. Yeah. Yeah. So in other words, we're losing information, right? So we are, the determinant summarizes information about the linear operator in that sense. So if we have a 6 is 2 times 3, but it's also 3 times 2. It's also 6 times 1 and 1 times 6. So there's all infinite many possibilities of different stretches. These proportion stretches would produce the same determinant. So the same change of the area by 6, but horizontal vertical might have different results, different coefficients. Okay, so determinant is good, but it cannot possibly contain all the information about the linear operator, even such a simple operation as a disproportionate stretch. You can do a disproportionate stretch differently, as a matter of fact, or proportionally for that matter, right? I could, how about square root of 6, square root of 6? That's a uniform stretch. And every square simply becomes bigger, and its area is multiplied by 6. Okay, so like I said, so loss of information. But nonetheless, it's a summary, so it's a good thing. If you put in something more complex information that requires 2 numbers, you put it in one single number, and it is meaningful and it's useful. Okay, so all right. So here's this is my rotation. That's interesting that matrix you see here, and the determinant is actually equal to 1. Okay, according to the Pythagorean theorem, we end up with cosine squared plus sine squared, and it is equal to 1. So once again, what it suggests to us is that rotation is, as we know, is a rigid motion. Okay, so this complicated looking matrix turns out, because its determinant is exactly equal to 1, that's a rotation without actually, because it's positive, there is no flipping. That's what it does. Pure rotation. Projection will give you a determinant equal to 0, as we already know. Okay, so every time you end up with 0, you know that. Also, think about the area, right? Well, what does it tell you? The determinant equal to 0. What does it tell you about the area? Well, the area is 0. So the area was 1 and has become 0. So that's what we're talking about here. Over here we had area 1 becomes 6. Okay, and on and on. Area 1, you know, when you have a flip, how is the area negative? Well, differently. So here in the number 3, the area kind of becomes -1. So we have negative areas, which is not entirely unheard of. If you remember calculus, that happens too. So in this collapse, in this case, the area, the square becomes a segment. That's what projection is. So what's the area of a segment? It has no area. It has length, but it has no area. So it has area, but it's equal to 0. So that's what it is. Area here is equal to 0. This area is equal to 1, and here area is equal to 0. So there is more to the determinant than just where it comes from. The determinant determines whether or not the operator is 1-to-1, but it contains more information. Not all the information, because after all, summary, it is never contains all the information. You had 4 numbers, and now we have 1. Naturally, you lost information somewhere. Okay, so this is the once again in summary, we have to. If there is a non-zero solution, then the determinant is equal to 0 and vice versa. And here it's a bijection. Remember the bijection, that's really a word that tells you all we care about here. It is in other words, for it is invertible. Okay, so it will be invertible if determinant is not equal to 0. Okay, I'll stop here, and so I'll see you after the break.